starting. So today's lecture is kind of a hybrid lecture. It's going to be an in-class, and we've got a couple, and hopefully there will be some more joining. I don't know why they have not. I think I have a conference ID or a meeting ID that I gave them one, and then an updated one. Hopefully they'll get it. Okay, so the plan today is to just continue with chapter 7, finish chapter 7 and start a little bit of chapter 8, maybe 3 or 4 sections of chapter 8, and we'll call it a day, okay? So last week I'm gonna thumb through the slides, and hopefully the guys online are seeing those slides, because I shared my screen. Taki, can you see those?
Yes.
Okay, thank you. So I'll just thumb through the ones that we have gone through before we I pick up where I stopped last time. We talked about exergy, and exergy, if you guys recall, is nothing more than the value of energy, okay? Energy is conserved, but the value of energy goes down. It's high in the beginning, and it goes down at the bottom. I mean, that's kind of the gist of that exergy situation. We talked about exergy, and we looked at the example of a fuel flame, and then we saw the entire thing in here, this entire system, which is an isolated system. The energy is conserved, but again, everybody agreed that the energy here is better than the energy there is better than the energy, because it is more useful. And afterwards we said, okay, now how do we quantify this? Okay, we went ahead and derived one equation, which simply says, and I'm just going to write the key equation that's really important. In order to find out what is the value of the exergy, there has to be a reference state, because it's really when you discharge, for example, hot gases to the atmosphere, well, what is the pressure of the atmosphere? What is the temperature of the atmosphere? So the bigger, what we agreed on last week is that the bigger the gap, the more valuable the energy is going to be. So the equation we came up with was an equation, so this is the key equation of this chapter, right? Which simply says that E, remember, E has a very interesting font. This means exergy per unit mass is equal to U minus U naught plus P naught, V minus V naught minus T naught, S minus S naught plus V squared over 2 plus G. Okay, it's obviously, because it's per unit mass, it's in kilojoules per kilogram. And then we looked at one example in how to calculate the exergy of saturated vapor at 120 degrees just by applying this simple equation, and then we came up with the answer. And then we also looked at this example evaluating the exergy of exhaust gas, because as you know, exhaust gas is really hot, and that means it has potential for energy. But once it's discharged in the atmosphere, that's it, it's gone. It's obviously higher temperature and a higher pressure, and we came up with an answer of approximately 368.9 kilojoules per kilogram. Afterwards, we said, okay, this exergy is with reference to a reference state. But what if you have two states and you want to find out how the exergy changes between the two states? So in that particular case, you can figure out the equation as being simple as E2 minus E1, and this is in the extensive part. It's going to be equal to U2 minus U1 plus P naught V2 minus V1 minus T naught S2 minus S1. Obviously, this is the third case. And then plus KE2 minus KE1 plus potential energy 2 minus potential energy 1. You may say, where the heck does this equation come from? It's more really not a big deal. You can find what E1 is. This becomes U1, V1, S1, V1 squared GZ1. And then you write another one for E2, in which case this will be U2, V2, S2, and then you subtract the two, and clearly this term will disappear, that term will disappear, this term will disappear, and the only thing you end up with is. So you have E2 minus E1, and obviously if the reference state is in here, right? This is 0, and it depends. If you are from state 1 to state 2, obviously the exergy at 2 is higher than exergy at 1, right? That means E2 minus E1 is positive. But if you are going towards the reference state, that means the exergy is going down to 0. Okay, and then we talked about the exergy balance also last week. And this is yet another equation that is very important. Is E2 minus E1 because you have a system like this. And remember what crosses the system is heat and work, right? So that vapor or stuff like that that's coming out to the atmosphere has to cross the boundary, right? Like the exhaust gases, you know, of a combustion system, something like that, they have to cross the boundary. So if you look at that first paragraph there, it says like energy, exergy can be transferred across the boundary of a closed system. Okay? The change in exergy of a system during a process would not necessarily be equal to the net. So if the exergy is crossing the system, the big question is, what is the exergy change of the system? It's very easy to go, well, the exergy change is simply equal to whatever is crossing the boundary. But really, that is not the case, because there is one component that has to be taken into account. What it says in here is that E2 minus E1 is equal to the integral between 1 and 2, 1 minus T naught over TB times delta Q minus W minus P naught V2 minus V1 minus T naught over sigma. Okay, what's the key thing about this? What it says in here is that this is the transfer, exergy transfer by heat. This is the exergy transfer by work. And lastly, this is the exergy destruction. So anytime you have an irreversibility, you have something like this, okay? So when you have an irreversible process, this is always going to be non-zero. So in other words, the exergy exchange is not always equal to the exergy transfer. It's only true in the case of very reversible processes. But if it is not, then you have to subtract. The difference is going to be really what the destruction, how the destruction was involved. Then we talked about every single term. The first one is the energy transferred by, exergy transferred by heat transfer. And remember what TB means. It's really the boundary temperature, because as the thing is going through here, is whatever the temperature of the boundary is going to be. And then work is the same. And lastly, E destruction is T naught times sigma, okay? So, and then we looked at an example again. Before we looked at the example, we said that E destruction can either be positive or zero, but it can never be negative. Just like entropy change, entropy production can either be greater than 0 or 0, but it cannot be negative. But the exergy exchange can be positive, can be equal to 0, can be equal, can be negative, depending on whether you're going far away or closer to the dead state. All right, so we looked at this example also last week, exploring exergy change, transfer, and destruction by looking at the water that we're bringing in from saturated liquid to saturated vapor, right, across the system boundary. And from there, we're looking at what is the exergy change between the two states, between state 2 and state 1. When it's the case, this is the situation. This is the equation to always use. And obviously, all these values are simply read directly from the tables. Okay, so it's nothing out of the ordinary here. Once we, come on. Okay, so we get the exergy change that's equal to 502.38, and then evaluating the one by heat transfer, it's again looking at the equation 1 minus T naught over TQ over M, and the temperature, and this is the temperature T naught, and this is the temperature T, and then EW, again, it's just plugging and chugging the values. And then we came up with the appropriate answer, at least for the destruction. Because in the destruction we got a 0 value, that means that the process is totally reversible. I think this is where we ended up last time, and now what we need to do is we look at the case, just like in the first law when we say that Q minus W is equal to delta E. The first law can also written in the rate form as Q dot minus W dot is equal to dE over dt. Okay, so this is kind of an equivalent way of looking at things when you have rate changes going on. So as in the case for the mass, energy, and entropy balances, the exergy balance can be expressed in various formats that be more suitable for a particular analysis. A convenient form for the exergy balance is simply, just if you look at this one, it's almost like you're saying dE over dt, right? So instead of having delta Q, you're going to have Q dot. Instead of having W, you're going to have W dot. Instead of having V2 minus V1, it will be dV over dt, right? See here, dV over dt. Instead of having E destruction, it's E destruction per unit time, that means E dot. So it's essentially just adding dots over all the terms, okay? So this is the general case. I mean, what's the usefulness of using the rate equation, you think? There is only one usefulness, is that sometimes you have a steady state situation in which nothing changes with respect to time, and hence you set this term equal to 0 and then you move on, okay? So the steady state form of the exergy balance is when you set this term equal to 0, and then you end up with sum of the exergy transferred by heat minus work minus the destruction is equal to 0. Okay? And write it here. 0 is equal to sum of 1 minus T naught over Tj, Tj being the boundary temperature, Q dot J, minus W dot minus E dot. This is for steady state. All right, closed system energy balance, destruction, and so most thermal systems are supplied with exergy inputs derived directly or indirectly from the consumption of fossil fuels. So in other words, the original energy, let's say for a vapor power system in the boiler, that's where most of the exergy comes in, right? And then some of it is being used to boil the water and this and that, and then as it goes through the system, some of it gets released. So accordingly, avoidable destructions and losses of exergy represent the waste of these resources. So you get a big certain amount of energy, part of it is used, part of it gets destroyed. So the whole idea behind exergy analysis is to find out what is it that we are destroying these energies to try to minimize them as much as we can, okay? By devising ways to reduce such inefficiencies, better use can be made of fuels. Now, most of these rest of this chapter essentially is done through examples. Okay, there are many of them. We're just going to do one or two for each section and then move on so we can carry on. I like this example right here. This is the wall of an industrial oven is constructed by sandwiching 0.66, 0.066 thick insulation having a thermal conductivity of 0.05 10 to the minus 3 between thin metal sheets. At steady state, the inner metal sheet is at 575 Kelvin and the outer sheet is 310. Temperature varies linearly through the wall, and the temperature of the surrounding is 293. You're asked to determine first what is it's to determine per unit area, essentially. What is the rate of heat transfer through the wall? What is the rate of exergy transfers accompanying heat transfer at the inner and outer wall surface, and the rate of exergy destruction? If you understand this example, that's really what you're kind of expected in general to know about this chapter, right? In addition to maybe this equation, you know. Let's look at this. The graph, this graph on this slide tells the whole story, right? So what do you have? This is the wall that we were talking about having a purple color, right? On the inside you have combustion gases, and then the metal strip in here is at a temperature of 575, and then at the outside is at 310. So what's the mode of heat transfer through this wall? Remember we talked about 3 modes of heat transfer? It's conduction. And if you guys remember from last term, the equation for conduction is Q is equal to negative K A delta T divided by delta X. Okay? So where the negative sign ensures that we're going from hot to cold. K is the thermal conductivity, A is the area, and this is the change in temperature, right? Because the temperature is coming in like this, and delta X is here, okay? The temperature here is 575, I think, and 310. So the change, see the slope of this line, is that positive or negative? Negative, that's why we have a negative sign in front of it to make it positive, okay? So finding what the heat transfer is going to be, and before we go on, what is the system that we are studying in here? What is the boundary of the system? It's whatever, it's the wall. It's what encloses the wall, right? So on the left side of the wall, you have heat transfer that's coming in. On the right-hand side, obviously, you're going to have heat transfer that goes out. So to answer the first question, what is the heat transfer? Looking at this equation right here, do we know K? Yeah, it's given, right? K is 0.05 10 to the minus 3. Delta T is what? Well, 310 minus 575, and delta X is 0.066. So when you plug, and what is the area? It's 1, because it's told you per unit area. Okay, so we just use 1 for the unit area. So this becomes, or Q over A is minus T minus K dt over dx. So it's, at the end of the day, it's 0.2 kilowatts per meter squared. That's the heat transfer that's going through the wall. Okay? The next question is, after we go heat transfer of 0.2 kilowatts per meter squared, the rate of exergy transfer accompanying heat transfer. You go like, I wonder what equation should I be using there, right? Remember, exergy transferred by heat is 1 minus T0 over TB, okay? First of all, what is T0 here? It's the surrounding, right? The temperature on the outside, isn't it? which I hope
Your dead state, right?
the dead state. See T naught.
Oh.
Yeah, it's 293. Okay, and what is the boundary temperature? Well, it depends if I'm looking at this boundary or this boundary, right? So when it's coming in, the temperature of the boundary is 575. Okay, so you see here, 1 minus T naught over T1, Q we already calculated, right? So we just plug 1 minus 293, which is T naught, the temperature times 2, and we find it's 0.1. So that's how much exergy is being transferred by heat through the first surface. How much is transferred by the second surface, the outgoing surface? The equation is exactly the same. T naught is the same. What has changed? It's just the temperature has gone down. Because the temperature has gone down to T2, which is 310, and goes like, oh, the exergy that's crossing that boundary is only 0.01. So you're coming in at 1.1, and you're leaving at 0.01. What does that mean? That means some of it has, the difference got destroyed within. Because, how did it get destroyed? Through irreversibility of the system. Okay? So now you see, of course there is no work involved in this problem, but you see that the exergy change is the exergy transfer minus the destruction. Next, in the next example, we consider a gearbox from an exergy perspective. To introduce exergy accounting, in which the various terms of an exergy balance are systematically evaluated and compared. So again, this is one example that we've seen, I believe, in chapter 2 when we were doing the first law. But look at the system. The system is really what encloses the entire thing, right? So, so what is the work that is crossing the boundary here? Obviously, there is work in, because the shaft that's coming in, does it surprise you that it's minus 60 kilowatts? It's negative because you are putting work into the system, but you get the output shaft that's bringing out 58.8. So what's going on in here? It's steady state, obviously. Q dot minus W dot has to equal to 0, so Q dot has to equal to the net Q has to equal to the net W. In other words, what is the net W here? 1.2, and it's no surprise that you have Q, which is equal to 1.2. Okay? So from an energy viewpoint, it says develop a full exergy accounting of the power input, okay? Where, again, the temperature T naught is equal to 293. So we come in and look at this and go like, oh, what the heck is the rate of exergy transfer accompanying? Come on. What is this saying?
Thank you.
Let's see.
From Zoom.
I don't want any gift. Oh, because I think we may be, I'm told, and I don't know if it's correct, running out of time, we've removed the 40-minute time limit in your group. Oh, love it. Okay, maybe I should get this. Because there is a 40-minute time limit, I'm told, by Dr. Bridge, right?
Yeah, I think,
He says he has to go out and then go back in again.
I think he had a subscription slot and just do.
Oh, okay. Well, if he uses it a lot, it makes sense. So we may still run out of time. Let's see.
You have to hurry up the lecture.
We have to hurry up. Yeah. So, boom, boom. So we got this, we got that, and so what in? Okay, now I lost my train of thought. Okay, EQ 1 minus T naught over TB. What is the temperature of the boundary? It's 300. T naught is given as 293. And Q dot is already known, so EQ can be calculated immediately, you know, which happens to be minus 0.03. The minus sign denotes exergy transfer from the system. Now, when you come in here, the rate of exergy destruction is evaluated using the exergy rate balance. Again, here you have W net is minus 1.2, as we said before. So E destruction typically is equal to E, because this guy is actually equal to 0. So it's going to be equal to E cubed. You bring this guy to this side, this is equal to 0, dE over dt. So then, well, I guess it's this one. Bring it this side, so it's going to be 1 minus t, it's going to be EQ minus W, right? EQ minus W, EQ was minus 0.03, minus EW is minus 1.2, so 1.17. When you do an accounting of this, you go like, okay, what is the rate of exergy that's coming in? It's obviously 60 kilowatts coming in because that's the input shaft, right? How are you disposing of that exergy, right? Well, the rate of exergy out is 58.8 because that's what the power output is bringing in, and through the low speed shaft, the stray heat transfer, the Q that's coming out of the shell of that gearbox constitutes an exergy loss, an exergy exchange, right? Which is 0.03, and the rest of it will be obviously destruction, so you accounted for the all of it. Okay. Now we move on to the next section, which I'm not going to spend too much time on because it's similar to the first one, except that now we are dealing with what? An open system. That's the only difference between the two. So when you're talking about an open system, that means you have to factor in what? The exergy coming in and the exergy going out, you know? So through the fluid that's coming in and the fluid that's going out. So when you do so, the equation, see how the previous equation looked like? It's exactly the same as this. Exergy transferred by heat, exergy transferred by work, exergy destruction. What are we factoring in? The exergy in, the exergy out. So nothing out of the ordinary in that equation. Now, in steady state, obviously the first term, the term on the left is equal to 0. And this equation can be simplified in terms of, not simplified, but this term E exergy F fluid in, exergy fluid out, or flow in and flow out, right? Those you can calculate using this particular equation as the enthalpy minus the enthalpy of the dead state minus T0 S minus S naught plus V0 squared over. So it's just a bunch of equations. So these terms will be calculated using that equation. Now, the steady state now can be written in more compactly in terms of the symbols. But the one that is most used is essentially this one. Okay, so EF1 minus EF2 is the enthalpy. This is for when you're talking about the exergy exchange between two states, as H1 minus H2, T0 S1 minus S2, and the rest of it. So the whole story, when you talk about open systems, is to evaluate that term. Lastly, although energy and exergy share common units, and exergy transfers accompanies heat transfer, energy and exergy are fundamentally different concepts. Okay? Energy and exergy relate respectively to the first and second law of thermodynamics. So if you want to go deeper, right? Why is energy related to the first law? Because energy is conserved. That's what the first law is all about, right? And in the second law of thermodynamics, we said that you've got entropy increase in entropy production, you know, when you have irreversibilities. So exergy expresses energy transferred by work, heat, and mass flow in terms of a common measure, namely work that is fully available for the lifting of a weight or a shaft or electrical work. In other words, all those irreversibilities are going to take away from the energy that is available to you. Okay, look, for example, here, this is just a comparison slide between exergy and energy and exergy of a control volume. Look at this control volume here. It's an open system, right? How much heat is coming in here? 90. How much work are you producing? 40, right? How much energy is coming in is 10 megawatts, and how much is going out is 60 megawatts. So when you look at the exergy, at the energy balance, if you will, whatever is coming in better be equal to whatever is going out. So how much is coming in? Well, what's coming in is 90 through heat and 10 through, whatever is the fluid is bringing in. So a total of 90 plus 10, which is 100. How much is leaving? Well, you got 40 and 60, so that's 100, so we're good. First law is, for open system, is satisfied. Now, when you look at this one from an exergy viewpoint, you go like, well, maybe I'm inputting here 60 megawatts of exergy through heat. I'm transferring 40 megawatts through work. This is the flow exergy in. This is the flow exergy out. So you go, okay, how much is coming in? Well, it's 60 plus 2, that's 62. How much is going out? 40 plus 15 is 55. So what does the difference imply? It implies that because of irreversibilities, we have lost 7. Okay, that's really all there is to it. There are 3 examples at the end that essentially follow this. It said the following example is to the use of mass exergy and energy balances for the evaluation of exergy destruction in control volumes at steady state. I'm just going to look at just the first one here. Exergy destruction in a throttling valve. Remember what throttling valve is? It's one of the examples of open systems that we talked about last term. And how does the enthalpy compare across a throttling valve? Anyone remembers? It's H at the entrance is the H at the exit is the same. Okay? So the H1 here, H at this section has to be equal to H at that section. You may go like, what in the world is that the case? Well, it's just a simplification of the second law for open systems, right? Which typically says that dE over dt is equal to Q dot minus W dot plus M dot H1 minus H2 plus M dot V1 squared minus squared minus V2 squared over 2 plus M dot G Z1 minus Z2. Okay? So under steady state, you know that this guy is 0. Is there any heat transfer through that little thing? 0. Is there any work done? 0. Is there any velocity change between the two? Usually pretty negligible. Is there any potential energy change between the two? Pretty negligible. I mean, no elevation change. So what do you end up with? This term is equal to 0, which means that H1 is approximately equal to H2. So it says superheated vapor enters the valve at 500 pounds per square inch, right here, and exits at the pressure of 80. So you're coming in at 500, you exit at 80. Remember what the goal of this is really for a pressure reduction. We would be using this in refrigeration cycles a lot. And it's asking you to determine the exergy destruction per unit mass of flowing, and obviously the dead state is given at 77 and 1 atmosphere. So how do we deal with this particular problem? Well, as I indicated, one thing that is important is that H2 is equal to H1 because it's a throttling valve, right? So we apply the exergy balance for open systems. Remember, in steady state it's 0. This is the exergy transfer by heat, exergy transfer by work, plus M dot exergy flow in minus exergy flow out minus exergy destruction. So perfect example that shows that longer equation that we talked about. Steady state, it's 0. Anything about the heat transfer, there is no heat transfer, so this guy is equal to 0. What am I talking about in here? There is no work, this is equal to 0. So dividing by the mass flow rate, so the exergy destruction divided by m is simply equal to EF1 minus EF2. And remember what we said, that for EF is simply equal to H, EF1 minus EF2 is H1 minus H2 minus T naught S1 minus T2 plus this plus that. Neglect, because it's a throttling valve, this is equal to 0. So we end up by saying that the exergy destruction is simply equal to the reference temperature times the change in entropy. There you go. Where do we get these values from? Obviously from the table, pretty simple. Okay, I'm going to skip the other two examples and then move on to exergy accounting. Is there a 6th section? Maybe not. Let me just check. I seem to remember that this is probably the end of it. So let's look at one. Okay, we just looked at this one. Yeah. Yeah, I'll let you look at the other ones because that's the same section anyways. So that concludes chapter 7. At least that gave us a little bit of an idea of what exergy is all about. Now I need to go on and look at this chapter, chapter 8, before we lose our session. So chapter 8 talks about vapor power systems. What is, in a nutshell, what are we going to be looking at chapter 8? It's vapor power cycles systems. That means we're going to be looking at cycles that generate power. How do they generate power? In the form of a shaft that is turned, right? Now, but how are we going to change that? Well, remember, systems exchange heat and work with the surrounding, right? So, to create work, probably be a good idea to have what? Heat. Right? Otherwise, how the heck are you going to get work, right? So, so that's really the idea: is to take a fluid, heat it up, pressurize it, heat it up to get a lot of thermal energy, and then pass it through some subsystems that are going to allow us to create work out of it. Of course, this is going to probably involve a boiler of some sort, a turbine of some sort, maybe a condenser, heat exchanger of some sort, and maybe a pump, you know, to keep the water flowing through the system, okay? So that's really what this chapter is all about, vapor power systems. We'll start in the engineering context by saying that the present chapter and the next, by the way, the next one will be vapor power cycles. In this chapter, we're just going to be generating power using liquid like water, and the other one will be air, pressurized air. The present chapter and the next are concerned with several types of power generating systems, each of which will produce a net power output from a fossil fuel, nuclear, or solar input. So we'll describe some of the practical arrangements employed for power generation, the one that I just mentioned a moment ago, which contains a boiler, turbine, condenser, and pump. You know, so those are the things, and then illustrate how such power plants can be modeled thermodynamically. So there are 6 sections in here. Last section, not really too important, but we will just say, because that's kind of what links it to chapter 7, if you will. But we'll talk about modeling vapor power systems, analyzing vapor power systems. One of the key cycles that you're going to be learning in this class, among I think 4 or 5 cycles, this is the first one, which is called the Rankine cycle. So the first 2 sections are really the key that describes how the key cycle works. And then afterwards, when we talk about 3 and 4, 3 and 4 is really how you are going to improve on the efficiency of such cycles. What modifications are you going to do? Okay. And then what is a regenerative vapor power cycle? And then talk about other vapor cycles, and then this. So what are the key 2 sections or 3 sections in here? This is really the first 2 or 3 of this chapter are really the key. That's what you're going to be held accountable for, right? I'm still going to talk about how we improve the performance, et cetera, but such things are usually not in exams for reasons that I will explain later. So let's look at some typical components of a simple vapor power plant. Okay? Simple vapor power plant will include, so you see the subsystem in here, A, right? This is where you're converting, obviously, so this is your boiler. This is the turbine, so your fluid is being pumped in here, energized and being pumped. And then this is a heat exchanger, so you're burning fossil fuel and you're adding thermal energy to your pressurized water, right? As it exits through here, it's coming out as very high temperature and high pressure. As it goes there, it expands through the blades of a turbine and it pushes against them. It creates a shaft that rotates, which you could in turn, hook up to a generator and generate electricity. Of course, this is not our job, right? Our job starts right here. We're getting a shaft that's turning. That means it's power. And then afterwards, obviously, you get the lower temperature and lower pressure gases that are still hot, by the way, coming in, but you don't want to pump vapor, right? So you want to turn that into liquid again by passing that through another heat exchanger. But how is that heat exchanger working? I mean, you can't just come in and be a black box and getting cooler water. Obviously, that heat has to be absorbed by something else. So what is that something else? Is that you're getting water from outside, right? And then pumping it in here, and then that heat gets thrown out through the cooling tower, and the combustion products obviously are passed through the stack and everything goes out. So this is fairly simplistic, but I think it tells the whole picture, right? What is the topic of this class? Is this subsystem that we're going to be studying, okay?
Why would
Go ahead.
this is kind of a tangent, but why would you throw away that energy cooling tower?
Well, that's what exergy is all about. You can use it for many things. Yeah.
It just seems wasteful.
Well, we will see that sometimes we reroute things, to preheat some stuff instead of throwing all of it out, okay? So that's why exergy, I think, is important to understand, because you got stuff that is hot, that's got a lot of thermal energy that is going out to the atmosphere. Why don't you reroute things through them, other subsystems, just to make use at least of part of it.
Right.
And that's a lot of engineers, that's what their field is, trying to kind of look at where am I losing things and what can I do to pull it out and make use of it. So subsystem A, which is this guy here, is where the important energy conversion from heat to work occurs. The function of subsystem B is to supply the energy required to vaporize the water passing through the boiler. Okay, subsystem B, which is right here, that's where you are vaporizing the water. The vapor produced in the boiler passes through a turbine where it expands to a lower pressure, which I just explained. The shaft of the turbine is connected to an electric generator, which is another subsystem. The vapor leaving the turbine passes through the condenser, where it condenses on the outsides of tubes carrying cooling water. I mean, that's how it gets cooled off. it condenses, and then now you get just liquid. The cooling tower or water comprises subsystem C. The cooling water is sent to a cooling tower where energy taken up in the condenser is rejected to the atmosphere, and then the cooling water is then recirculated through the condenser. Okay? In subsystem A, we observe that each unit of mass periodically undergoes a thermodynamic cycle as the working fluid circulates through a series of 4 interconnected components. What is the 4 interconnected components? Boiler, turbine, condenser, pump. Now, okay, now that we know at least what it goes through, right? Now we need to put some math to it, right? First one, all the fundamentals required for thermodynamic analysis have already been introduced. So it's nothing new. We're not going to learn any new things. We know how to read tables. We know how to read, if we know what the state is, we can go to tables and read the values, right? So now how do we connect those values to what the system is going to be? So remember, boiler here, turbine, condenser, pump. Okay, so that's kind of the path of my thing, and this is obviously work done with the turbine. Obviously the pump also uses work, so we call it WP, right? So this is the Q out, and this is Q in, right? And that's how the cycle actually works. They include, so the fundamentals that I'm talking about include the conservation of mass, conservation of energy principles, and the second law of thermodynamics. That's why we spent some time in the first thing to talk about the first law, the second law. These principles apply to individual plants of the component as well as the more complicated overall plant. So each subsystem in here, or each component, will have to satisfy conservation of energy, conservation of mass, or the entire thing also. Now, this is the subsystem that we're talking about: boiler, turbine, condenser, and pump. And stray heat transfer between, so what are the idealizations we have to make? So this is the interesting part. The stray heat, remember when the vapor comes in through here? Do you think that the shell of that turbine is going to be a little bit hot? I mean, you got pretty darn hot gases that are coming in. When you take heat transfer, you know that heat always flows from hot to cold. It doesn't matter. I mean, these are like metal pieces and this and that, so you're going to have some heat transfer, right? So what are we going to consider? We're going to consider that stray heat transfer between plant component and their surrounding is neglected. In other words, Q is only occurring here and here, but nothing there and nothing there. That's idealization. I think they are reasonable. Because even if there is a Q here, it's going to be nothing compared to the Q that is involved there or the Q that's involved in here. First. Number two, kinetic and potential energy changes are also ignored. And each component operates in steady state. I mean, we're not talking about the moment we turn things on, but you know, after it gets to the steady state regime. Now, before we look at this slide in here, let me ask you a couple of questions there. By the way, the state entering the turbine is always called state number 1.
Just by convention?
By convention. This is 2, this is 3, and this is 4. Okay? Now, let's take a look at it. Do you agree that each one of these components is an open system? Sure, because it's got an inlet, one exit, one inlet, one exit, right? And remember that equation for the first law? In steady state, dE over dt is 0. equals Q dot minus W dot plus M dot, right? H1 minus H2 plus V1 squared minus over 2 minus V2 squared over 2 plus G Z1 minus GZ2, right? Kind of that first law written for open systems. Now, let's look at the boiler. Let's look at the turbine, okay? This is 1 and that's 2, inlet, exit, right? For the turbine, is there any heat? Let's simplify this equation for the turbine. 0 equals, what is Q dot? 0 minus W turbine, right? Plus M dot is the mass flow rate, times H1 minus H2, right? Remember, we are neglecting potential energy, we are neglecting kinetic energy, right? So based on this, what can I say? That WT over M is equal to what? H1 minus H2. Okay. Now, let's apply this to the condenser. Condenser. Just take a look at that equation. 0 equals what?
Still 0.
Because you have E. So you would have Q.
I will have Q,
Yeah.
right? So it's going to be Q out.
Plus M dot.
There is no W, right? Right?
No work.
Plus M dot times
H1 minus H2.
H2 minus H3.
H2 minus, remember, this is inlet,
Oh.
exit, right? So it should be H2 minus H3.
2 minus, okay.
Okay. I should have called this inlet, exit, right? So based on this, now one thing we did in here is this really Q out?
No, it's just Q, isn't it?
Well, we'll call this Q out. Remember sign convention? If you add heat, it's positive.
Right.
Oh, so it's negative.
So it's negative Q.
You know, if Q is an absolute value, I would better call it minus Q out, right? So based on this, if I bring Q out to this side and then divide it by M, what do I get?
H2 minus
H2
H3.
minus
H2.
H3.
See, it's the same thing as equation number 2. And how about pump? For the pump, 0 equals,
Work.
there is no heat, so 0 minus W pump, right? Plus M dot times what?
H4, right?
Remember, H inlet minus H exit. So what is it?
H3.
H3 minus
H4.
H4. Right? So based on this, what is so 0 plus M dot H1, so how come my sign is
If there's work being done to the system?
Right, isn't the sign
Is that
the wrong way?
positive then, technically?
so this is work done,
To the.
It's going in, right?
So that's
on the
negative
system.
work, right?
yeah.
So then it would be a positive?
So
Still work on the system, but when you move it over, it'll be positive.
so minus W, so here, for example, we kept it as,
Right.
oh,
Right.
That's
so
what I'm
sorry.
That should be
confused about.
positive.
That should be positive,
Okay.
because we are doing work, thank you, yeah. Minus, we're doing work on the system, that means, okay?
Let's say you get H.
That's how you get the
4 minus
H3.
H3.
Okay. So now we go WP. Now I'm going to show you a way to, without doing any of this stuff, to get what those values are very quickly. But it's kind of important to go through it one time. So if I do this, then this gets switched, right? Last but not least is the boiler. What do I have about the boiler? 0 equals Q, Q in, I guess, right? There is no W, plus m dot times h4 minus h1, you know, h4 minus h1. So based on this, hopefully, I will have qn divided by m dot is equal to h1 minus h4. Two significant things about these. You go like, holy, everything depends just upon the enthalpies of the substance of those four states. In other words, if I know H1 here, I know H2, I know H3, I know H4, what can I tell? What information can I get from just reading those values from tables? Number one, can find out how much work the turbine is doing. Two, how much heat is lost through the condenser. Four, how much work the pump is using up. Five, how much heat I'm adding up to the system. Six, efficiency. Then I can find what the network is that I'm getting, right? What is the network? This is a very key. When somebody says network, that means there are two places where at least two places where work is traversing the boundary, right? So you need to get the net one, you know, in other words, the out minus how much you are paying. How much we're paying for work is really this. So the network is WT minus WP, right? To find the efficiency, we take that network divided by Qn, we get the efficiency, and many other things, okay? So, look at that slide. When I come here, if I didn't have to do all this, I just come in and go like, okay, turbine. What does the turbine do? I say, the work done on the turbine, and I ask myself, is it H1 that is higher than H2? What do you think? Is it H1 that is higher or H2 that is higher? H1, why? Because you're coming in with pretty darn hot vapor, right? Pressurized. So the work done by the turbine is simply H1 minus H2. There's no, you cannot say it's H2 minus H1. You know, you're getting something that is absolutely, to get something positive, it has to be this minus that. How about here? Q out at the condenser. Which one is higher? Is it H2 or H3? H2. So the absolute value, right, of Q out is essentially H2 minus H3. How about you come here to the pump? Which one is higher? Is it 4 or 3? 4, because you have pressurized. That means that the work done on the pump is H4 minus H3. See here, that third equation. And lastly, in these two, which one is higher? H4 or H1? It's obviously H1. That means that Qn has to be H1 minus H4. Okay, so it kind of summarizes that. And then after we get those values, number one, the thermal efficiency is equal to, remember, the net output divided by the input. What is the net output? Is the work done on the turbine minus the work of the pump divided by Qn, right? So again, efficiency is just a function of all those H's. And the network output equals to the network input. Why is that? The net heat input. Why is it that the network output is equal to the net heat input? Remember, for cycles, remember the first law, delta E equals Q minus W. What is delta E for cycle? What is delta E of a cycle?
0.
0, because you're coming back to the same point. That means that Q cycle is always equal to W cycle. Never forget that. That's why we say that the network output, remember W cycle is obviously the network output, and this one is the net heat input. Why are we saying the net heat input? Because there are two places across the boundary where we are exchanging heat. One is taking heat in, the other one is taking heat out, and therefore there is a net heat input. So again, eta can be calculated either one using either one of those two equations. And the heat rate is the amount of energy added by heat transfer to the cycle, usually in BTUs to produce a unit work, usually kilowatt hours. Okay, so these are just units. There is another key word in here that you probably haven't heard about. It's called the back work ratio, the BWR. What is it? It's another parameter used to describe the power plant performance. Back work ratio. In this power plant that you see here, we're producing turbine work, but we are expanding, if you will, right? Pump work. Now, do you want the pump work to be high or do you want it to be low? Low. Do you want the turbine work to be high or do you want it to be low? Obviously. So you want WT to be as high as possible and you want WP to be as low as possible. So how about the ratio then? So you want the ratio to be as low as possible, okay? That's what we call the back work ratio. So it's defined as the ratio of the pump work to the work produced by the turbine, and then WP over WT, because it's a mass flow rate that goes through them, you know, this simplifies, and you get H4 minus H3 over H1 minus H2. Now, and usually that value for when we deal with incompressible fluid, that value is fairly low. If the fluid, now we'll talk about the ideal Rankine cycle. If the fluid passing through the various components of the simple vapor power cycle without irreversibility, frictional pressure drop would be absent from the boiler and condenser, and the working fluid would also flow through these components at constant pressure. Also, in the absence of reversibility in heat transfer with the surrounding process. Okay. So this is another key part in here. How do you think this heat transfer is occurring? Usually what happens is this fluid is being carried over by a piping of some sort, right? And for those of you who have taken or who are taking fluids, you know that if fluid is flowing through a pipe, even if it's a horizontal pipe, just to make a simple assumption, is there any pressure losses between the inlet and the outlet? So at the inlet, the pressure has to be higher, right? That's what causes the flow. That's what sustains the flow, because the flow is always subjected to some friction, because the fluid that is against any solid surface is being stopped. And because the fluid is Newtonian fluid, there is a shear stress that is created against it. Now, if we assume that there is no friction, the fluid, as it flows through the boundaries, just slides across the boundaries. So, does that create any pressure losses? No. So, we will assume that here, P is constant. It's obviously not true, but it's idealistically, ideally, I should say, we can call it that. And because here it's also a heat exchanger, we call this pressure P equals to a constant, right? But how about here and here? Here we know that there is no heat transfer. We are assuming that Q is equal to 0. And here we are assuming that Q is equal to 0. And it's reversible. Remember, when Q is equal to 0, that means it's adiabatic. When it's reversible, that becomes then isentropic, right? Why? Remember, ds is equal to delta Q over T. So whenever there is no heat transfer and it's reversible, then S is constant, and here S is constant. So for an ideal cycle then, an ideal vapor power cycle is composed of what? So P is equal constant is an isothermal, right? Isobaric, right? Followed by isentropic, followed by another isobaric, followed by an isentropic. Okay? So, an ideal Rankine cycle, this is by the way for a Rankine cycle, ideal, right, is going to be 2 isotropic and 2 isentropic cases. Because we are dealing also with a water that's being vaporized and it's coming back to liquid again, that means we're working in the vicinity of a dome, right? So if you look at the dome like this, on a maybe, I'm not going to do a TV diagram, I'm going to be doing a TS diagram because isentropic is easy. That means it's a vertical line, right? So typically what happens, as you come out, remember you're working between 2 pressures, right? 2 pressures like this. Ideally, you would start here. At what state? All your liquid has become vapor, right? So state 1, remember, is always the entrance to the boiler, to the turbine. So, and you're coming down between 1 and 2 as in, what is isentropic? Isentropic with a lowering of pressure, that means I have to drop how? Vertically down, okay, because I'm on an S. You know, I come down like this. I end up at station number 2. Then what happens at 2? Between 2 and 3, I'm passing my vapor through a isobaric. Remember, this line is a constant pressure, right? And ideally, you would be going until all the vapor becomes liquid. So maybe you should end up right there, right? Ideally. That's state number 3, right there. And then what do I do between 3 and 4?
Go back up. But you-
Between 3 and 4, I'm pressurizing. I'm pressurizing how? Isentropically, because S is constant. So the only way I can move is vertically up, right? So I'm going to move up, up until, why do I stop here? Because that's where I hit the higher pressure. Okay, so I call this point number 4. Right? Number 4. And then what happens between 4 and here? Here you have kind of compressed liquid. Now you're adding heat to it. So what's happening? Because it's just liquid, you are increasing the pressure, you are increasing the temperature. How? At constant pressure. Until I get to this point. Then what happens? Which I call this point A. What happened at point A? It starts to boil. What happens to the, now I continue at that same pressure, right? Now what's happening is a phase change that's occurring until all the water becomes vapor and we're done, okay? That's what the ideal Rankine cycle is all about. 2 isentropic processes and 2 isobaric processes. So let's see here. Area 1, B, C, 4A1. Remember, the area under TS curve represents what? what's the area under the PV curve represent?
Plot the pressure, that's work.
It's work. And T versus S represents? What's the cousin of work? Heat. No? So P and V gives you work, T and S gives you heat. So the area here between 1, B, C, this and that, that's the heat added, you know, the heat added right here because we're going in that system. Whereas the heat that goes from, the area that goes to BC3, you know, this heat here is the heat that is removed at the condenser level. So the difference in the two areas, right, is essentially the net heat that is added to the system. The enclosed area, 1, 2, 3, 4, A1, 1, 2, 3, 4, A1 can be interpreted as the net heat input, or equivalently, the net heat output, because we're talking about a cycle. And the work done on the power, by the way, on the pump, can be evaluated using this equation as an approximation, because you're going between 3 and 4, you're going to assume that V is approximately constant, right? And then you just multiply the specific volume by the pressure change, P4 minus P3, and you should be able to get the actual value. So let's take a look at, okay, I think we already described that the cycle is made up of an isentropic expansion, constant pressure, isentropic compression, and another constant pressure for section number 4.1, okay? This example, number 1, is maybe the most important of this entire chapter. It's the first one. You need to be able to reproduce that very easily, by the way, okay? You should be able to analyze an ideal Rankine cycle with no problem. Because remember, as I used to tell my students, analyzing a Rankine cycle is nothing more than finding what the 4 H values are. The rest is a walk in the park, right? So here, you're told that you have steam is the working fluid in the ideal Rankine cycle, and saturated vapor, you know, right here, enters the turbine at 8 megapascals, and saturated liquid exits the condenser. In other words, it exits right there at a pressure of 0.008 megapascals. And you're told that the net power output, notice in here it says the net power output is 100 megawatts. Does it mean that it's really WT that's equal to that? It means it's WT minus WP that is equal to 100 megawatts. So just based on these two pieces of information, you're told what kind of liquid it is, the peak pressure, the lower pressure. Look at how many questions you're being asked to answer. 1, what is the thermal efficiency? What is the back work ratio? What is the mass flow rate of the steam in kilograms per hour? What is the rate of heat transfer, Q in, as it passes through the boiler? What is the net rate into the condensing steam as it passes through the condenser? What is the mass flow rate of the condenser cooling water? You know, but 6 questions. So how do you treat problems like these? You always have to draw the physical system and then the TS equivalent to it, okay? And you will be told when you're given exams to say, okay, draw the physical exam and then the TS diagram. This is what is expected for an ideal Rankine cycle. It's always going to be the same. The only thing that's going to change is maybe this pressure, that pressure, right? Mass flow rate, if any, but everything else should be the same. So you're always going to have a boiler, you're always going to have a turbine, a condenser, and a pump, okay? And remember, don't miss this. State 1 is the entrance to the turbine. Why am I insisting on this? It's because all the equations that are in the book are based upon that order, okay? So if you suddenly decide that 1 is here, you're messed up, totally, okay? So I'm going to repeat it as many times as I could, but always remember that. One is the turbine, and then you go on. So this is the TS diagram, and remember these are the two isentropic processes, and these are the two constant pressure processes. Where do we go from here? What's the first thing? The first thing is always to, before you can answer any question, is to really figure out what those H values are.
Just looking at the Rankine cycle, starting with isobarics, it's same constant pressure.
Yes.
But your pressure drops when you go through the turbine.
Yeah.
So is that?
No.
When you pass through it,
when you pass through it,
right.
yes. Yeah.
So that isobaric is prior to the.
It's prior to this.
Okay,
Yes.
okay.
It's between the boiler here and the turbine.
I'm just out of sequence by one
Yeah.
step. Okay.
Yeah. So, what are we given? I mean, finding the things are probably not going to be a big deal. First of all, it says to begin the analysis with fix. You have to fix the states. The first one, the first state should not be a problem at all. Why? Is it well defined? Yes. Why? Because I'm given liquid and I'm told it is saturated vapor. So it's the pressure that is given to you. So you use table, which table? The 3. And then you just look at that pressure, and then what do you read for this value here? You read the value of S. Well, first of all, you need the value of H, G, but at the same time, you also need to read the value of SG. Why? Because you need to apply it to here. State 2, you only know the pressure. Remember, you need another piece of information, which is what? Which is the S that corresponds to this. Right? Now, so we go to the first one. When you go to table A3, you read that H1 immediately from there is 2758 and S1 is 5.74. And then so state 1 is done. Okay, it's already 1/4 of the problem solved. Now, state number 2 is fixed by this lower pressure and the fact that the specific entropy is constant for the adiabatic internal irreversible expansion to the turbine. So again, using saturated liquid and saturated, because you know that state number 2 is within the dome. So what do you need to find, what property do you need to calculate? Quality. There's no ifs or buts about it. If you know S here, do you agree that you know for this lower pressure, you can read from the table SF and SG? You know S, that means you can calculate the quality immediately, which you can be done in here. Why do we need the quality? Because we need to know what the value of H2 here is, which is what? HF plus X times HG times HF. So a prerequisite to that is to find what the quality is, which we're calculated here at 67%. Then we can apply it to find H2. Now, 2/3 done. And then state number 3. State number 3 don't have to do anything. It's just HF for the lower pressure. So it's an immediate read. And then lastly, H4, remember that equation that I told you before? Remember H for this guy, for the pump, H4 is equal to H3 plus W divided by M, right? So H4 is equal to H3 plus WP divided by M, where WP over M, you use that approximation that I told you about. It's really the V at this location times P4 minus P3. Okay? So H times P4 minus P3. Needless to say that units are important, okay? To make sure that we're getting exactly the same stuff. Now we get H4. By the time we got to here, we got all the H's. Now it's just a walk in the park, really, to find what the answers are. The first one is, what is the net power? I go, oh, net power, that means it's the power produced by the turbine minus the power produced by, used up by the pump, okay? So the power by the, remember those equations that we, of course I erased them, right? You know, remember when we were looking at this, you can figure out what those are, you can just read them directly off your stuff. This is the work done on the turbine, this, they have functions of this, done. Okay, finding the efficiency it's again the net power divided by the Q in, and you find that it's 37%. The back work ratio is the work of the pump divided by the work of the turbine, again, in terms of the H's. And then you find that 0.84%, it's pretty good, you know, it's about 1%. And then mass flow rate of the steam can be obtained from the expression for the net power, because the net power is given, which is equal to m times this. So from here we can get the mass in kilograms per hour. And then what is Q in? Again, it's all a function of the H's. Once we know m dot, H1 and H4, we just multiply, we get those. And the mass and energy rate balance applied to control volume enclosing the steam side of the condenser side. Again, Q out is no big deal. And then W cycle is Q in minus Q out. Oops. The only thing that may be of interest in here is the last part where it says in the condenser, to cool the condenser, what do we typically do? We run a mass flow rate of cold water, you know, coming in from outside and going in here. And obviously here you have a mass flow rate that's coming in for the water. And then it's just an energy balance between the two, because the Q here is equal to m dot times H2 minus H3. You know, that's the Q out of the condenser, but the Q out of the condenser has to be taken out by the cold fluid that's coming in. And the cold fluid that's coming in will have mass flow rate of the cold fluid times enthalpy out minus enthalpy in. You know, this is enthalpy out minus enthalpy in. When you do that, then you can figure out what is the mass flow rate of the cold water. So I urge you to look at this example. If you want to do a good review of this chapter, maybe reviewing this first example, I cannot do it independently, kind of, and see if you reproduce those values. I think you'll get great confidence if you do that, and at least learn it. So they didn't kick us out of this thing, so which is good. 25, 2 more. So, the big question now comes in. What happens? It says thermal efficiency of power cycle tends to increase as the average temperature at which energy is added and by heat transfer is increased, or the average at which heat is rejected. Anyone can tell me what the cardinal efficiency, do you remember that? Eta max, remember, is 1 minus T. Is it TC over TH? Well, remember, for a power cycle, let's say that we forgot how the heck to do it, right? So what does a power cycle do? Power cycle would have Q in, right? Q out, and then it will have a work, which is Q in minus Q out, right? So the efficiency is W, which is Q in minus Q out divided by heat in, which is Q in. So this is 1 minus Q out over Q in. So this is obviously the hot reservoir, this is a cold reservoir. You remember, when we go from an efficiency to an ideal efficiency, we replace the Q's with T's. So this becomes Q out is TC and QH, Q in is TH. So I was right in here. Okay. Now, to increase TA, to increase efficiency. Increase efficiency. Do you agree that if TH increases, what happens to this ratio? It gets smaller. That means 1 minus something that is smaller is something that is bigger, right? Does that make sense? Or we can decrease TC. If you decrease TC, that means you are subtracting something smaller from 1, and therefore you are keeping most of the pie, if you will. Okay? So a way to increase efficiency then is to either increase TH or decrease TC, or do both if you could. Okay? Let's take a look at how those really work out. Where are we increasing, where are we adding heat in here? We're adding it through the boiler right here, right? So if I increase the pressure of the boiler, because if I increase the way if you remember cooking, with a pressure cooker, obviously, right? The more you increase the pressure, the more the boiling temperature goes up, right? So to increase TH, what do you need to do? You need to increase the pressure of the boiler. So if you increase the pressure of the boiler, graphically speaking, this is the original state, 1, 2, 3, 4, 1. Do you agree? Do you all see this? Now, if I increase the pressure, then my starting point goes to where? Saturated vapor has to kind of shift to 1 prime, right? Now I come in 1 prime, 2 prime, 3, 4 prime, 1 prime like this, okay? Now, why is this increasing thermal efficiency? Because the temperature, look at the average temperature here of heat addition. Do you agree that I'm adding heat between 4 and 1, right? Between 4 and 1. So this is the temperature, so maybe I'm increasing the average temperature, which is going to be somewhere there because this one is a little bit lower. Do you agree that this may be the average temperature of heat addition? It would have been just this if there wasn't this part, right? This guy tends to pull it down a little bit. Now, because this guy was pushed up, do you agree that the average temperature of heat addition has gone up by increasing the pressure? Okay. So increasing boiler pressure then leads to an increase in thermal efficiency because TH will be increasing and therefore will be increasing the efficiency. How about the other end? If we decrease now the condenser pressure, because we want to decrease TC, so we need to decrease the pressure. Again, instead of finishing as 1, 2, 3, 4, 1A, because I decrease the pressure, now I finish at 2 prime prime. I come back like this, that. Now what happens to, again, my lower pressure, my average lower pressure, instead of being this, now it's this one. That means that TC has gone down, okay? Again, decreasing the condenser pressure tends to increase the thermal efficiency. Which again, just by looking at this equation, we could have made those statements. Now the ideal Rankine cycle, which is 1, 2, 3, 4, 4 prime, and 1. Here we have the 2. This is the ideal Rankine cycle. This is the Carnot cycle. Carnot cycle has 2 isothermal processes and 2 isentropic processes. It says the ideal Rankine cycle has a lower thermal efficiency than the Carnot cycle. Why is that? Because for the Carnot cycle, the average temperature of heat addition is right there, is TH. But for an ideal Rankine cycle, it's the average of this entire line, which obviously has to be lower than TH, right? So having the same maximum temperature, TH, and minimum temperature, because the average temperature between 4 and 4 prime is less than TH. Despite the greater thermal efficiency of the Carnot cycle, so this Carnot cycle, you may go, it has high thermal efficiency, but it's got issues, okay? It has 2 shortcomings as a model for a simple vapor power cycle. One is combustion products not cooled as much, and state 3 prime is a two-gas, two-phase mixture. Okay, I'm not going to spend too much time on the first one because, well, I guess the next slide actually explains it. The problem with the key problem is here, normally you would have a pump in there, right? But here you're pumping vapor and liquid, which is not desired, right? So that's not going to be, conceptually it's good, but you know, you cannot make it happen physically. Okay. All right. Another thing here is, as illustrated by process 1-2, an actual adiabatic expansion through the turbine is accompanied by an increase in entropy. Here we're talking about isentropic processes, but in reality, nothing is really isentropic. You have to, when you have inefficiencies, you're producing entropy, and therefore you will have a little bit of entropy increase, right? And these are the two that we talked about towards the end of chapter, the previous class, when I said we're going to be using them later on. They are called isentropic turbine efficiency versus isentropic pump efficiency, okay? They may look like very complex things, but really their only use is to really figure out what is the value of H2 when you have H2S, okay? So, and the idea behind that is that when you have an isentropic efficiency of the pump, right, which is usually less than 1, that means that if the pump is not highly efficient, it's going to produce less power, right? Because, you know, it's going to have some losses or irreversibilities associated with that. And if a pump is not isentropic, right, it has some inefficiencies, obviously it's going to use up more power, right, to make the pump work. So it's not only will have the pump, the power that is needed to work the pump, but part of the power that needs to fight or to overcome those inefficiencies. Okay? Well, we're going to look at a couple of examples later on how to use these two terms. Now, I think this one, the reason I like this chapter, the way it's been done in this book, it repeats exactly the same example as before. Same value, same everything. The only thing we are introducing here is that there is an inefficiency of the turbine. So you have a turbine efficiency of 85% instead of 100%. Okay? So what do we do with that? We start with state number 1 exactly the same way as before. And then we read the value of S1. Then we come in and go and try to find what the value of S2 is, right? We have to use, in that case, see here we read H1 and we read S1, same thing as we did in the first problem. The specific enthalpy at state 2 can be determined using the isentropic efficiency, you know, equation 8-9, and therefore eta T is equal to H1 minus H2 divided by H1 minus H2S. Remember that H1 is already known. H2S, right, is the specific enthalpy of state 2 on the TS diagram, right, which from example, you know, assuming that H2S is isentropic, that means 1791 that we get from the previous table. We plug it into this equation, that everything is known except that H2 is not known. So what is the goal of this isentropic efficiency is really to find what the value of H2 is when H2S is known. So instead of using H2S 1794, now it's going to be a little bit higher because there was some inefficiency that was associated with the turbine. And then the rest of it is exactly the same. H3 is the same, H4 is the same, and then answering all the rest of these equations is exactly the same. Okay? And one thing you would probably notice is that the efficiency that was 37, I think it was 37% or something like that before in the previous example. Now, it's no surprise that it's going to be a little bit lower because you have some inefficiency that is associated with the turbine. All right, I'm just going to do, I think, this section and then we'll stop. I think they've been really generous and they didn't. I think I lost one online thing. Tracking still there. Good. How do we improve the performance? Okay. The representations of the vapor power cycle considered thus far do not depict actual vapor cycle power plants faithfully, for various modifications are usually introduced. We know that an increase in the boiler pressure or a decrease in the condenser will result in reduction in steam quality at the turbine. I guess the first thing to notice in here is the following. Remember before we start from state number 1, this is the entrance to the turbine, and then we come down like this, okay? The first big problem is this. As you go from 1 to 2, what does typically happen? You got this vapor that's coming in, right? It's saturated vapor, the pressure is going down, and here you're going through the blades of the turbine, right? But what do you think is the quality of this? As you're going down, the quality is going down and down. So let's say at this point you have a lot of droplets of liquid that are coming in with, and droplets of liquid have mass in them. Very high pressure, very high velocity, they come in and hit the blades, what causes? What can they cause? They can cause, they can erode, erosion of the blades, deformations of some sort. So how do you solve this problem, for example? Okay, it says, if the quality of the mixture passing to the turbine becomes too low, the impact of liquid droplets of the flowing liquid vapor mixture can erode the turbine blades, causing a decrease in turbine efficiency, and of course an increase in maintenance, etc. So the rule of thumb is that you need to have an efficiency of a quality of 90% or more, okay? So you don't need to be anywhere deep into the game. So people said, okay, maybe the reason for this is, instead of starting from state 1 in here, maybe I should start from state 1 right there. So that means I start from a superheated state instead of saturated state. Okay? Then, as I come down here, right, at least I'm coming, you see, I'm mostly in the vapor, and even if I enter the dome, I'm probably going to be pretty darn close to the saturated vapor line, and maybe have an X that is greater than 90%. Okay? That's why one method of improving the performance is called the superheat. See here? Instead of going from 1, 2, we go from 1 prime to prime. So as we are not limited to having saturated vapor at the turbine inlet, further energy can be added by heat transfer to the steam, bringing it to a superheated vapor condition at the turbine inlet. But how the heck are we going to do that? Because you're passing the vapor through a boiler, so the most you're going to get is vapor. How can you get superheated vapor? You can only get superheated vapor if you get vapor and then add heat to it, right? Or pass and superheat it, if you will. Or a reheater, or it's called a superheater, okay? So this is accomplished in a separate heat exchanger, called a superheater, which is boiler per superheater is called a steam generator. In fact, when you have a problem that talks about steam generator, that means that you are starting from this state here, 1 prime instead of 1. Okay? So the cycle with superheat has higher average. See, what's the other benefit of starting with superheat?
Higher temperature.
Higher temperature, because now you got this leg that's bulging up into higher temperature, so technically your average temperature will go up. So the cycle with superheat has a higher average temperature of heat addition than the cycle without superheating. So you can say that I'm gaining also a little bit in the thermal efficiency. Superheating tends to alleviate the problem of low steam quality. See here, instead of ending up at 2, you're ending up at 2 prime, which has a greater value of quality than 2.
You need a more efficient condenser though as well, right? Because you're starting at a higher.
Yes. Yeah. But here, obviously, we are hitting. We're trying to solve a problem, but we're gaining another added benefit, which is a little bit of increase in the I thought I had the figure here, but I guess I don't. Another word about this reheat, okay? Another way, a further modification normally employed in vapor power plants is called the reheat. So this one that we just talked about is called the superheat, right? This one is called the reheat. With a reheat, a power plant can take advantage of increased efficiency that results with higher boiling pressures and yet avoid low quality steam at the turbine exhaust. How does that work? And then you go like this and go like, come on, what's the deal? So this is the part that I said I'm not gonna give you a problem like this in exams to do. But I think it's an eye opener when you look at it and try to figure out what does this mean? Okay? Let's first start with water coming out of the pump. Okay? We're pumping it, right? Coming it into a steam generator. Steam generator here, remember, you're coming in and generating state number 1. By the time this guy comes out, right? It comes out in a superheated state. Okay? It comes out in a superheated state, which is right here. Then what do? You go through a turbine, right? But the turbine is not a single stage turbine, it's a 2-stage one. Okay? So you expand it initially through the first turbine. Obviously, you're not going to go from the highest pressure to the lowest pressure. You're going to expand it to somewhere in between, an intermediate pressure, which we call this pressure here. And then what happens? And then the product that you get, of course, you're doing it isentropically, so you go from 1 to 2. Remember, 2 is the intermediate pressure. And then what's happening at 2? You're passing it through the heater again, so you're reheating it. So as you reheat it, do you agree that it's reheated at constant pressure? Because remember our basic assumption, any flow through a pipe is a constant pressure thing. But the end result would be just a temperature increase. So you increase it now to temperature number 3, to temperature T3, as it exits the reheater. And then you expand it through the second stage turbine, which brings you down to that state, and everything else stays the same. So you go like, okay, so what's this benefit that I'm getting here? This business that I'm doing like this is causing 2 issues. First of all, it's increasing my temperature, as opposed to just coming down directly. Now I'm coming down and doing this, but my quality is going up. So when computing the thermal, says the steam does not expand to the condenser pressure in a single stage. The principal advantage of this thing is really just an increase in the quality. You see, instead of just dropping down directly to 4 prime, by reheating, I'm just pushing it a little bit to the right. Okay? So it's really an increase in the quality of the steam at the turbine exhaust. And then everything else stays the same. Now when you look at this, you go like, What is the difficult, if any, the difficulty of analyzing this versus the previous one, versus the ideal Rankine cycle? The ideal Rankine cycle involves how many states? 4 states. How many states do you see in here? Well, get 1, you need to evaluate 2, you need to evaluate 3, you need to evaluate 4, 5, and 6. 2 additional states. But, it's no big deal, but still on 2 additional states nonetheless. Okay? Supercritical cycle. Again, the temperature of the steam entering the turbine, obviously remember TH needs to be as high as possible, but the steam entering the turbine is restricted by metallurgical limitations imposed by the material used to fabricate the superheater and reheater. I mean, you cannot just put in any temperature that you want. It has to be sustained. High pressure of the steam generator also requires piping that can withstand high stresses at elevated temperatures because you have thermal stresses that get developed. Although these factors limit the gains that can be realized through superheating and reheating, improved materials and methods of fabrications have permitted significant increases in thermal efficiency, and this has progressed to the extent that vapor power plants can be designed to operate with steam generator pressures exceeding the critical pressure of water and turbining at temperatures of 1100 Fahrenheit, so it's pretty healthy temperature. Let's see here. Okay, so just look at this example and I think we'll call it the day.
Did you say a problem like this won't be on the exam?
Yeah, the exam not going to give you something that requires many states like that, but in the homework I think that will be.
Okay.
Not that they are difficult, it's just that they are too long and tedious, So if you can figure out 4 states, that's good.
So how many stages in a typical steam plant? The 2, or is it they go higher?
Sometimes 2, sometimes they have multiple, like 4, 5, But the problem with having multiple things too comes with its own price, because you get many turbines that you have to maintain, many losses, and this and that. And the big question is, how worth it is it? How much worth it is to do. It's always nice to have theoretically as many as possible, but at some point you go like, no, it's too much problem to have so. So we just looked at this supercritical thing. Just look at one quick example. Steam is the working fluid in the Rankine cycle with superheat and reheat. So this will be kind of another good example. Steam enters the first stage at 8. So anytime you have a 2-stage, that means you have a high pressure, the low pressure, and an intermediate pressure. Okay, and expands to 0.7. Then reheated to 440 before entering the second stage where it expands to the condenser pressure of 108. The net power is 100 megawatts, and then answer all these little questions. And again, once you draw the physical, see, I keep stressing this, it's always good to draw the physical things and annotate where the states are. And these numbers have to correspond to these numbers that are on the TS diagram, just like one next to the other so you can see. And it's easy for me to look at this and go like, I'm starting from the superheat, expand through the first turbine to the middle, to the medium, intermediate pressure, and then I'm reheating, and then I'm dropping down, and then going to 4 to 5, through the condenser until I get saturated liquid, pump it up to pressure at 6, and then go back again to the stuff. So when you draw it like that, you can visually see what you are doing. And the idea behind solving these problems is that you have to determine the H values at all these different points. It's really always fixing the states, and probably that's going to be the place where you have, once you find those states, instead of just proceeding, it's always a good idea to go back and make sure that my states are correct. Because if they are incorrect, everything that you calculate is, the equations are right, but everything would be incorrect, okay? So, to begin, we fix the principal states. Of course, when you have the pressure, the initial state, which is in the superheated region, the pressure is given, the temperature is given. You get those two, you go to table A4, boom. You can read immediately the value of H1. Why do you need the value of S1? Because remember, you have an isentropic process, right? Then it's a tedious thing. You are marching from one state to the other, to the other, to the other, to the other. That's really all there is to it. And the best way to be good at this is to really do these examples kind of independently, you know, then you can do. If you can do those, if you can reproduce these, you can do any problem that involves vapor power cycles. I mean, that's my simple opinion. If you know the logic, I read the value of S1, I'm going to the other value, find what the quality is, then I keep adding and moving and find out, are you still in the dome? Did you maybe move into the superheated region, et cetera, like in this case, state number 2, you know what the intermediate pressure is, you know what the entropy is, so it's fairly clear that you can find what the, you know that the S value is between SF and SG for that particular pressure. That means where are you? That means you are within the dome. That means if you are within the dome, that means you have to calculate the quality. If your S happened to be greater than SG, that means you are the superheated region. So that's one of those things that you have to do. In this case, we're pretty darn close, you know, almost 99%, right? And then specific enthalpy finding, once you find X, you needed to find what the enthalpy is. And then state number 3, you know, superheated vapor with P3 equals 0.7. The temperature is given. Again, you find that you are in the superheated. It's the same broken record, right? Really, it all boils down to finding what those states are, okay? So when I think I'm gonna stop here first. I think that's, at least it's better than canceling the class. So I feel much better about that. So when we come back next week, we will finish this chapter. In fact, it was programmed to span 2 weeks anyways, you know, so we'll do this one. We will finish this chapter next week and we'll start on the vapor power cycles.
Is that 9?
Which is 9, yes.
First exam the week after next?
And the week after next. And then next week we'll do some review to kind of